Good afternoon, and welcome to IOT402. This is optimizing supply chains for smart agriculture from the farm to the table. So we've heard a lot about the farm, and we are living in a time lapse this week. So for part of the data, what we're going to talk about in this session. My name is Asif Khan. I've got the CEO of Industrial IO with me, Jason Massey, and the CTO of Industrial IO, John Crawford. And they're going to talk in deep about Industrial IO and their story and how they've built their platform. John is going to talk and take us through a platform they've built, Context, which is basically the data platform on IoT, and how do you use the data that is made out of IoT in a contextually aware manner. And then we'll wrap it up with what is different in IoT architectures that we should look at, like from traditional architectures and things like that. So with that, I'll invite Jason Massey on the stage. Yep.
First, I want to start by thanking Asif for inviting us here. He's been an awesome champion and friend for us since we started the business. Since this is Vegas, I'm the opening act. I kind of get everything warmed up and ready to go for the main event, which is our CTO. Let's see. So our story starts with a very fundamental question that any industry is asking. How do you do more with less? We're good at reducing waste from an energy standpoint, but you also have to increase productivity. See some screenshots of our software. As we started the company, we were a group that went and actually did industrial energy efficiency projects. So we would upgrade the lights, the HVAC systems inside of the factory. Inevitably, the CEO of these enterprises would say, prove your energy savings to us. And that brought us down the path of developing our own energy management software system. Lots of energy management software systems out there. You guys have probably heard of companies like Internoc and others that are kind of leaning more towards working with the utilities to work with industrial facilities. What's different about us is we are the agent of the factory. That's our customer. We like to game the utility system on behalf of the customer, not for the utility. But simply, what we're finding is commercial energy management systems weren't translating to the industrial factory sector. So the regression analysis that you typically do in a commercial building is weather, right? A commercial building will behave a certain way in the summer versus the fall versus the spring. But when you look at factories and you look at industrial facilities, the real regression analysis that you want to do is production normalization. So where do you get production data? That required us to go tap into really crappy legacy ERP system, warehouse management systems. That's where we had to go get this data from. So we ended up saying, well, we're just going to build this ourselves. So we ended up building software. We needed that data context. Remember that word, Asif had used it earlier. We'll come back to it. But at the end of the day, even though we started getting into pulling in legacy data, deploying temperature sensors, vibration sensors, humidity sensors, kind of this real funky world of new technology and legacy technology, at the end of the day, we come back to it's a unit of energy. So we like to use this. What we'll talk through is an energy system that's pretty significant, mass that's kind of hard to comprehend, and hopefully with our software, we're able to kind of process this data at light speed and actually make it useful for our customer base. So the case study that we're going to go through today is Lineage Logistics. This is the second largest cold chain in the United States. It's 113 facilities that average about 500,000 square feet per facility. So what do we do with 30 atomic bombs worth of energy? Hopefully something good. So what we do with that energy is we actually feed the population of the United States and keep food from spoiling. So Lineage does about 25% of all food that's produced in the United States flow through their facility at some point during the year. An interesting little tidbit, in one of their facilities in North Carolina, last Chinese New Year, they shipped 10 to the 9th power chicken feet, froze it, and then shipped it to China. We won't go into as we dig into these warehouse management systems, we learn a lot about the types of foods that get produced and frozen, and yeah, we won't go into those details. This kind of goes into what John's built with the context system. So Lineage will blast freeze in California 4 million pounds of strawberries a day. The blast freezing process is very energy intensive, and that's how we got pulled into the project with them. Another kind of point of context is all the strawberries that we pretty much consume in the US get produced in a 12-week period. So time is not our friend in this case, and so it's a race against time to bring together that data very quickly and create operational context very quickly through alerts. And that's what John's going to walk you guys through. It's a little pixelated, I'd say, for security reasons this happened, but I just pulled a bad screenshot off of one of my other decks. We're still negotiating with Apple whether we can use this iOS. We needed to build a platform for ourselves to rapidly develop applications for large enterprise customers to ingest all these different IoT sensors and make it a developer-friendly format. So we don't have to do the customization. We can push that back towards the customer itself. So we really see this as a true industrial operating system. Whether we get to use iOS in the future is yet to be seen. I'll turn this over to John real quick. There you go, sir.
Okay. So I'm John. I'm the CTO at Industrial IO. General title is usually biggest nerd in the room. That usually resonates a little bit better. So this iOS thing that we've created, the reason why it exists today is because as a startup, we have 6 developers to 8 developers, depends on the day. And in order to create these apps really quickly, we have to create a system that we use ourselves so that we can iterate really fast. So this is something that we came up with about 1.5 years ago. And so far, so good. So we'll get into the kind of logistics of it. So it's kind of broken down like you would see in any other kind of OS. So you have apps at the top where you can create, in our case, we have an energy management system called Insight, where you can go in and view data about different kinds of systems. And we've actually had another third-party developer develop an application for Lineage called Metrics One. So they've brought in labor data, revenue data, warehouse management data, and put it on a KPI dashboard. So in order to do that, we had to have a kind of structure to where we could work in teams. So Industrial IO, we did the back-end side of things. So we brought the data from the source systems into our system, or their data lake, as they call it. And then we pass it off at the database layer to the third-party developer through the APIs and applications that they built. So in order for us to be able to support this, this is generally how things are laid out. So you have apps at the top, you have SDKs at the bottom that do a lot of different things. We generally like to call these data stacks because it's not just an SDK in this case. It's not as simple as that. And we kind of segment things into the logical groups. So you have files, rate schedules, weather, a way to organize facilities and call centers, real-time data, alerts. So there's many more that you can create. But one we're going to focus on today is alerts. So what does a data stack or an SDK actually look like? So we start at the bottom. So you have workers. They do dirty work. So a lot of the times in these industrial facilities, things aren't very convenient. So it kind of depends on how you get that data. We have cases where there's an SFTP server set up somewhere. We have to pull data from there. We have like the WMS systems. We pull that from the source systems in Omaha or wherever. And they can also do things like organize data in a better way. And the layer above that is the stream processing and analytics layer. So you process the data that you've brought in. We use Storm quite a bit. You could also use something like Spark or, in this case, IoT. And kind of the purpose of this is to take in all that data and kind of make sense of it and organize it in a way that you can extract it from a database or a through a database and API. So middle layer is the database. This is where data sits. So you can use Cassandra, RDS, anything, something like that. You have APIs that are built on top, and they provide an interface for the applications above to access that data. Within an actual data stack, you can also have a specific kind of application that is just geared towards reading that app and organizing data further, so that we can kind of monitor and administer certain things. So when you're looking at the alerts data stack, it really comes down to this group of technologies. So at the bottom, with the workers, you have Lambda. You can, in this case, we use AWS IOT for a lot of the heavy lifting. Use SNS to make delivery a lot easier. We use RDS, Postgres for storing the alerts and keeping track of what exactly you need to be alerted of. You have an events API that you use to write rules for your alerts. And you can also store your dependencies in there, so when an alert is triggered, you look to see what other things you need to look at. We'll get further into that here in a minute. And then you can have an admin app on top. So through this use case, essentially what we're going to be looking at is a blast cycle. So a blast freezer is essentially you're freezing something as fast as you possibly can, because the faster you freeze it, the better the quality is when you thaw it out. So it's a very energy-intensive process, and this is kind of a picture of an analysis that the data team at Lineage Logistics did to kind of visualize what exactly is going on. And essentially, if you kind of visualize this, say take this room, cut it in half, and it looks like a big garage, essentially. And you have a bunch of fans on one side, and they just shove in cold air and pull the heat out. That's essentially all it is. You have like a little garage door that comes down in front to where when you're done loading it, you just shut it, and then you go at it. So that's kind of the gist of what that is. And so kind of the tricky part about blast cycles is, one, it's a very energy-intensive process. Two, it's really hard. It takes time to figure out how long stuff should be in there. So the data science team has come up with a certain range of things or a certain range of times for certain materials. So strawberries in 50-gallon drums, or squid in boxes, or strawberries in 5-gallon drums. So each one of them will freeze a little bit differently just because of the way the air flows. So in order to optimize this process and reduce cost and freeze stuff fast, you've got to it kind of boils down into these things. So the first facility we went into, it was Oxnard, California. The rate schedule there is probably the most complicated rate schedule I've ever seen in my life. It's based on the weather from the day before. So essentially, I'm not sure how many of you are aware of how energy is billed, but essentially, if you think of it as water, the faster or the more you turn on the spigot, the more water is coming out, so therefore the higher the rate. And they charge based on that rate. So in this case, so KWH is billed like if you have a gallon of water, so you're saying every gallon of water I want to charge this rate. During the day, that changes 24 times. So every hour of the day has a different rate schedule. And if it was really hot in downtown LA the day before, then it's going to skyrocket. So typically, in North Carolina at least, you pay about 10 cents per kWh. To put this into perspective, certain days of the year in Oxnard, California, it costs about $4 per kWh, which is absolutely insane. So we want to take that into account. So we want to keep track of what rate is going to be charged at the next hour. We also want to consider what we're actually freezing. And there's certain parameters around that we may want to adjust. So if I'm freezing squid versus strawberries, the freeze times are going to be different. So I've got to look at that. And the next thing is I want to determine how much time is left whenever I try to make a decision on whether I should shut down the blast cell or not. So at a certain temperature and a certain time, it's okay to shut down the blast cell for a little while, just because the It's like if you have a bunch of cold stuff and there's a warm center, then it's gonna radiate into the middle. So it's okay to pause it for a little while. And so we're gonna use that to our advantage and figure out when we want to shut it down and when we want to continue going. So you're kind of doing it, you're making a trade-off here. So this is the nerd diagram. So here's what's going on, how the data generally flows. You have your streams coming in to AWS IOT. You have the events API setting up rules. You have Lambda doing dirty work. You have Amazon machine learning at the bottom making the decisions. So once you gather all the data, you're making some sort of decision at the end of the day. And then you're going to use SNS to actually deliver those alerts. So it's one thing to detect when something needs to be shut down, but it's another to say, okay, this guy in this facility needs to know this, and he needs to know it pretty much immediately, so that he can start. You can't just like shut down a refrigeration cell in like a second. So you've got to get it out and make people aware of it as fast as possible. So we're going to break this down. I don't expect you guys to understand this whole thing. So you start at the API level. Say you have some kind of query language. AWS IOT actually makes this super easy because a lot of people know SQL. So the way you set rules is via SQL. So if we look at this, at the first alert that we want to create, say based on previous analytics, we've determined that the optimal blast cycle for 300,000 pounds of California squid using this certain kind of packaging should be 48 hours. So say we know that. So essentially what we're going to do is using this query language, we're going to set essentially what is a timer, but you're really just triggering a time where AWS IoT is like, okay, I want to look at some stuff. So here I do select star. We'll get into what this actually does here in a little bit. And then it's kind of nice because I have an alert ID that is being referenced in the events API and have that stored in the database. I want to be able to reference that whenever I trigger that alert. So I'm inserting that alert ID into the SQL call, and whenever I have that event being triggered, I can pull that out of there. And the other thing is for our purposes in this case, when real-time sensors come in, which is a refrigeration system, we give them a naming scheme. So things/devices/3027. So say 3027, I know it doesn't really mean a whole lot to you guys, but it means an ID in the database that means, okay, 3027 equals this blast cell. And then we're going to look where a timestamp is greater than that number. It's an epic timestamp, but just say it's noon on some day. So the second thing we want to look at is we want to take into consideration the electrical rate. So the electrical rate is very important in order to determine whether or not we want to shut it down. So say it's going to go to $4 per kWh. It's going to cost me X amount of dollars to shut down this blast cell, and it's going to delay more stuff coming in. There's a cost associated with that. But in this case, we're going to read it from the rates from the rate schedule stream, ID 36 things/rates this time instead of devices /56, and we're going to look at the individual rate field, so where it's greater than 50 cents. So essentially what we're doing is we take that into the events API, and then we write that to AWS IoT. So we tell the rules engine in AWS IoT to look for this. And the kind of the next piece of this puzzle is how the data comes in. This is kind of a common problem with anything to do with IoT, at least from what we've seen. So you have the easy stuff where you have sensors out in the field. You have a refrigeration system somewhere that's pushing you values every, say, 15 minutes. You have electrical rates that it could be hourly, like in Oxnard, and there's a place in Georgia like that as well. It could be less frequently, like 4 times a day. So those are kind of your TOU structures to where, say, from 10 to 2 in the afternoon, it's going to be this rate. From 2 to 6, it's this rate, and so on and so forth. And then you have flat pricing, where this is mainly in residential spaces, but you just always have a flat rate for energy usage. So say it's 10 cents. So the issue is here, the rate schedule is predicted either, if you're having real-time pricing, it's predicted the day before. And the closer you are, the more accurate it is. But there's other finite ones that you don't have to predict. So for Santa Maria, California, they're on a different utility. I can pretty much say at a random day next year, this is going to be the rate. So you got to figure out, how do we take that non-real-time feed and turn it into a real-time feed? That's where the worker logic comes in. It's like you're essentially taking a non-interval based data feed of some sort and turning it into like a data feed. So every hour, you have a worker that runs on an interval and says, okay, I'm going to take my rates and I'm going to emit what the rate is for the next hour. So that's kind of the hard part about all this stuff, is when you're combining different kinds of data and you're trying to add that context, it really, your intervals are not your friend, essentially. So take the worker push. So you take the rate schedule, you push them. So for rate ID 56, 57, so on and so forth, you're going to emit that on the hour, and that goes through MQTT to IoT, and then you can just treat it like a stream, just like anything else. So as an example, this is what a payload of a rate message looks like. So you have the rate ID, 56. You have a time range in which it's good, so random time, say noon to 1 for this case. There's actually good or real dates, bonus points if you actually extract that. You have a period ID, which is pretty much like, this is the period that is good for this specific time. Then you have the rate, then you have the unit. So dollars, I'm not even going to get into the different currencies, so you could have whatever there too. With the real-time data stack, this can come from refrigeration feeds or EMS feeds, but this is essentially what it breaks down into. Pretty much any time series thing always comes down to a timestamp, key and a value, and some kind of special identifier. So in this case, the special identifier is 3027. The timestamp is that. You have a field name. So in this case, we really care about blast cell enable. This pretty much determines whether the blast cell is still on or not. You have a value, which could be any data type. Then you say what the type is, essentially. So these are the things that are coming in here. Just kind of think of them as just a continuous stream. You're always looking at every value. So every value, as long as you have a rule set up in IoT, it's going to be looking constantly, and it's based on that SQL engine. Oh, sorry. So say we've detected that one of the rates is 0.75, so 75 cents. A rule is triggered. We then, in order to actually tie things together, you need to take it to something like Lambda, because essentially what you've got to do is you've got to start looking at device shadows, because you can't really combine streams in that way. So each trigger is just that one piece of payload. So this one message within the refrigeration system data is what triggers it. Now, if you were doing something simple where the rule is where you're just looking for 75 cents greater than 50 cents, great. But that's not really a value add in our case. You've got to add context to the data and actually make sense of it. So this is kind of where we are in the system now. So we've triggered a rule. It goes to a Lambda function, and now we have to actually get into the dirty work. So what do we do? So the first thing is we need to ask the events API for more information about the alert. So if I'm Lambda, I'm just looking at a specific piece of payload, I need to ask the events API to say, hey, is there any other alert that is dependent on this trigger? So in this case, there is. You need to start looking at the actual blast cell data as well. So step number 2, is you need to actually look at a device shadow for the blast cycle data. So I'm looking at my last known value for my refrigeration blast cycle. So number 3, we can reach out to a different system. I didn't want to go out and document all this other stuff, but essentially number 3 is you have some API somewhere, call it the ops metric API or the metrics 1 API, which is the project we were talking about a while ago. You've got to figure out what's in the blast cell. So in order to do that, you call the API and say, okay, this output ID associated with this refrigeration cell, and it does some magic and says, okay, we've got 300,000 pounds of California squid in rectangular containers or something like that. So we take all that data and we bundle it up. And Lambda, we don't want to put all the logic here in Lambda because we may want to adjust something. So we need a little bit more smarts. So we tie in Amazon machine learning into this. So you can pass off the information in a known format. Statistics nerds do their thing and say, okay, we do or do not want to turn this blast cell off for this amount of time. So we say, just for the example's sake, we do. So number 5 is we trigger the alert. So now we need to talk with the events API again and say, okay, we're going to trigger this alert, and then the events API can go off and do its own thing, maybe call another Lambda function, or maybe talk directly to the AWS CLI. In this case, we talk directly to the CLI to say, okay, this event has been triggered. We have everything kind of set up in SNS, does its thing. So this is kind of going into, I think something got out of order here, but say, just for the example's sake, the blast cell's been on for 38 and a half hours. So it made a decision to say, okay, I want to turn it off. So here, sorry, I forgot that I broke this down. So number 3 is talk to the production API. I've kind of already gone through this. So information we sent off was rate 75 cents per kWh. It was on for 38 and a half hours, and there was 1,500 cases of squid. So we trigger it or ignore it. So we trigger it. So now the events API has a list of user subscriptions. So say in our events API, we have a list of users that belong to the system. So that's stored somewhere else. And we have links to say, okay, this person cares about this specific alert. Whenever they create that subscription, we write that to SNS. So every alert essentially has its own topic. So here you have alert stream 36. So that's specifically just for that alert. And we also have an alert stream 65 for the facility. So essentially what this is in order for us to have people subscribe to things they care about, we create these essentially feeds of things that are going on. So in the top case, we have a stream specifically for this alert. So if I'm in Macon and for some reason I care about when blast cycles want to go off in Oxnard, I can subscribe to that if I want. And I would say, okay, I'm specifically going to look at that one. But if I am the general manager at Oxnard and I just want to see generally what's going on so I can kind of get a gist of what's going on with my facility, I can subscribe to the 65 stream. So that means that everything that goes on in Oxnard, including this alert, will be available in that stream, and I can get whatever kind of notification I want to do. So with SNS, you can set up text messages, or you can actually, for this case, we've actually set up an Apple notification application. So we have a little iPhone app that says, okay, I belong to this facility, and every time I want to get an alert, I get it on my phone. You can actually set all that up in SNS, and you just push it to an SNS stream just like anything else. So now that we've optimized our blast cycle, essentially this is what's going on. So if you look at it on a graph, so maybe you want to pull this into Insight, for instance. So here for this date and time, we see that it's gone above 50 cents. So we can actually put a little state there that says, okay, I turned off my blast cycle during this time, and I put a little shadow over it that showed that this is something that we avoided. So we can actually calculate how much money we actually saved by saying, okay, we reduced our kW load by X amount. So kind of the moral of the story here is, say we shut it down for 5 hours, we saved a lot of money in energy as well. So it allowed the grid to level a little bit more, like that's what utilities like. But it also preserved the quality of the food, so it didn't affect the food in any way, based on all the statistics nerd type things that we've done with machine learning. So the next steps with this, so if I want to optimize blast cycles further, there's a lot of things we want to do with machine learning quite a bit more in order to create these real-time type things. So it actually gives you a really nice interface for saying, okay, I can have some statistics guy at Lineage go and optimize this algorithm, and then I can make it better the next time I run this alert. So some other use cases you could do here are monitoring health of equipment. So if you have, you can start doing predictive things to where you're looking at certain fields within a real-time stream, and it can help you save a lot of money by knowing having a better handle on how your equipment is running. Kind of one of the next big things that we also want to do is plug in transportation data. So with Lineage, they have obviously a lot of trucks going around everywhere. So being able to tie all that data into AWS IOT, and then we or people within Lineage can say, okay, now that I have this stream of data for transportation, I can do a lot of things with it. So AWS IoT really allows us to add that flexibility for the users, because data scientists still understand SQL, and they understand how to interact with machine learning or Amazon machine learning, so they can do a lot of things with that as well. And now I want to hand it off to Asif.
Thank you, John. Really cool stuff. I've known Jason and John for 3 years, and they've made massive progress and kind of paved the road for a lot of people to look at these things and move in this direction. So I wanted to touch a couple of things that John touched upon. One is blast cell. When do I get it started? When do I shut it down? When you think about that, a wrong decision costs a lot of money. To start that thing and shut down the thing costs lots of energy. Even from a sustainability perspective, that's a decision you want to get right. Maybe not all the time, but most of the times, and make sure your supply chain is optimized. The second thing I wanted to talk about or touch on was the food wastage on the supply chain, and we had done a study with the customer they're talking about, is 30% of the global food produced goes to waste. And when you look at that, we produce enough food today in the supply chain to feed the population. And we need to get better and efficient at, again, this is according to studies that were done. To get better and efficient, we need to optimize the supply chain and reduce the waste. So gain efficiencies in the supply chain. When we think of waste as individuals, as families, it's amazing that we really care about food on our plate. But when you look, and the thing that gets kind of missing is when it's produced to the warehouse, to the port, to the distribution center, to my local grocery shop, what is happening there? And that's where industrial comes in with that context aware. And when you look at that data, where is all that data? That data is locked up in your production systems, in your order fulfillment systems, in your CRM systems, on your logistics systems, on your transportation systems. Until you cannot marry the IoT data with this context, all of that data is just data sitting there. And I've seen tons and tons of use cases where silos are built, and then we gain a little bit of efficiency and go on. In this case, really we are moving the needle in moving it the right way and moving forward. So with that few data points of what Lineage or industrial is doing, let's talk about why IoT architectures feel different. Now, things are not static assets. So what does that mean? An Amazon fresh truck that is coming to drop the grocery is talking. It's breathing and living. It has data that you can use and mine to gain that efficiency in that supply chain. So the sustainability part of it is using that data to get better at making sure that the last mile is done. Tesla is another great example. Like, there are people who are looking at data that is emitted from Tesla to predict the maintenance behavior, for example. How will this do? Upgrading software remotely for a car. That's unbelievable. Like, 5 years ago, you could go into your ODB2 port and put a jack and get all your data out for your driving patterns. Insurance companies, for example, like, I think there's one insurance company where you can buy by the minute, by the mile, and depends on your driving pattern. And these interesting use cases are getting enabled because the things that we are using today are giving us so much data to really make smarter decisions and really gain efficiency. The other big shift that has happened is the customer has gained many identities. For today, like in the old days, an individual was a customer, a business was a customer. But in this case, when you look at Prime Now, we service Prime Now with some of the contract drivers from Amazon, for example. Now, who's the customer here? There are different types of identities for the customer: the contract driver, the end user, or even, let's say, if my wife orders orders the shipment and I receive it at the door, that identity is kind of getting pervasive. So we need to learn to or use that data to deal with it. Cool one, Amazon can drop packages, or Amazon is piloting dropping packages in Europe with Audi and DHL. So when you look at that, the concept of an identity linked to a user is being challenged in the IoT space. I can give you a code, for example. I don't know how they do it on the Audi use case, and remotely you can open the trunk, just give access to the trunk to the driver. Those things are being fundamentally challenged, and that's where IoT is pushing the boundaries. And because of these small gains in different places, you have like small and massive gains you're having in different places, what is happening is it's enabling industrial and companies like industrial to think of the problem in a whole different way and give us efficiencies which we have never seen. One of these things that closest to my heart is my home is almost an enterprise right now. And what that means is this. Like, you look at this and you say, I can talk and order stuff on Amazon.com. I don't have to think about, for example, when my dishwasher runs out, when my utility runs out, and the dash button kind of reorders it for me. I have to program it. My camera is talking to the internet. My sprinkler system is talking to the internet. And I can control all of that from Alexa. That's kind of cool. So the security around this, the scale around this is amazing. Like, when we talked about scale in the past, we would think about scale of an enterprise. But now imagine the global population, and every home is an enterprise. We have to think of it as an enterprise. Each of these devices are talking to us and saying something to us. And how do you make sense out of that? Machine learning. Today morning we talked about Poly, Lex. These are things which enable you to go to the whole different next level. So I did preface all of those slides to come to this slide. What is it that we are like fundamentally different here? In traditional web architectures, or even the modern web architectures, some of the things we took for granted, for example, reliable network. I'll get the speed I get because I have the connectivity. The servers are there, like it's in my data center, or it's in a remote location, or on the cloud. It's there, it's always there. And if it falls down, I call up somebody, and that guy, it's his job. We always had stateful transactions. Like, I come from the ERP world, so like in my past life, and we used to think stateful, like the transaction is stateful, and the Java Beans conversation around that. And the IP address was one of the most fundamental ways to talk to a system. Like, I know from a DNS resolution, I can go talk to this server. This is my website host, and things like that. But IoT, or the device capabilities are challenging that in ways like, for example, like the warehouses that they were talking about, some of them are in remote locations. Some of them are in locations where there's great traffic, but because of the acoustics of that, you lose network in places. And so you get this bursty behavior, this intermittent behavior, and how do you deal with that in real time to get data? Let's say a data scientist is doing this, looking at this great graph, and then for 30 minutes, for some reason, he lost that data on that cell segment, and the temperature dropped by 5 degrees there, or it heated up by 5 degrees. So in that corner, like in the far off corner, everything that I stored is gone. So we need to start thinking of dealing with this problem. We touched on devices are geo-dispersed. So each of these warehouses have, like I've seen some of the facilities where you have sensors in like a cube of like 5 by 5 feet. Now they are like geo-dispersed in a location, across locations, across different parts of the planet. And then this is not new on the cloud. This is like stateless transactions. If you talk containers, if you talk microservices, stateless transaction is how we were born. Like everybody is thinking in the cloud, and that's how we deal with it on the cloud. But for IoT, it's imperative to think stateless. If I tie back my IoT communication to a state, dealing with that intermittent traffic, keeping the payload small, making sure that if the payload actually goes through the latency is going to be hard. If somebody cracks it, that'll be amazing, but that's like, you cannot be dependent on states on the device, for example. And then there are no IPs. Like, that's the biggest one. These are devices which are basically like beacons or sensors which are talking to us MQTT now. So how do you deal with that? Now, these are challenges, I would say, that are thrown at us as engineers, and industrial, and a lot of companies like industrial are trying to solve this. The other big piece of all of this, that was one device. Imagine all those challenges on one device. Now when you extrapolate that problem across thousands and millions of devices, it becomes a whole different problem at a scale. So when you look at that and say, how do I architect for one device? Now, okay, how do I architect that this scales for millions of devices that are geo-dispersed? That changes and challenges very fundamental architecture beliefs that we've had for a while. We released AWS IOT like last year, I think, or a couple of years ago. It's a fully managed service, and industrial has been on this journey, and they've been like paving the road kind of in a way. The device in this state, in this is the wind farm, the windmill, talks to the authentication server, the security we talked about. All of the security pieces of IoT you can probably tie back to AWS IAM and the construct of AWS that you know. The device gateway is a mechanism to ingest that data, or how do you say, talk to AWS IoT. And then you use the device shadow as a thing for, or a representation so that you can talk to it, like John was talking about when he talked about alert streaming and things like that. You have APIs to access them. You can build applications on top of AWS IoT. But you can extend this using Lambda, using SNS, using other services that the platform like AWS provides, and take it to the whole next level and leave the undifferentiated heavy lifting down to us on the AWS IoT side, but really take your imagination to the next level. What is that next big application that will really be for greater good for the humanity? And secondly, which scales at a level where we can deploy millions of these sensors and still be okay with the reliability and promise to our customers, yes, the food is good. The food that is up in the distribution center at the Walmart, at the Amazon Fresh truck that is coming, I'm not picking up the food anymore. It comes in a bag now. The food that came to me is actually good, and I feel good about it because I know the whole supply chain was optimized and is getting optimized every single day. So with that, thank you for coming to the session. We'll wait around for a couple of questions. So if you have any questions, please go ahead.